8. Okay, so let us get started. Well, so before we begin, so today is the deadline for one of the popular machine learning conferences I clear. So all my TAs are busy with their submissions. So I decided to do it myself, so that we don't cancel this. Okay, so I'm going to do the tutorial today. So we are going to talk about Scikit-Learn, which is a machine learning framework in Python. Okay, so I think in your first assignment, also in your second assignment, like, so you are implementing things from scratch, but there are obviously a lot of packages out there in Python, like, which you could use for running some of these algorithms. Okay, so Scikit-Learn is one such popular framework. So we will also learn about another framework called PyTorch in the next tutorial, but that is a bit more low-level framework when compared to Scikit-Learn. So we're going to see several features of Scikit-Learn today. It is a popular machine learning framework, which, as we will see today, have almost everything that you need to just plug and play and try. Okay, so here you see that they have different classification algorithms implemented, different regression algorithms implemented. We haven't seen other types of machine learning problems like clustering, dimensionality reduction, like, and they also have model selection algorithms like k-fold cross validation, bit search, etc. And they have a lot of pre-processing, like, features, like, which some of them we will use today. Okay, so let's get started. So I shared the collab notebook for everyone in the chat. So the only issue is whenever new people join, they won't see what is shared. So I will share once in a while for people who are joining late. Okay, so there's a question in the chat already. So are we allowed to use these frameworks on the assignment? Okay, probably the timing of this tutorial is a bit misplaced. You should not use this in your second assignment. Okay, so the reason why we are doing this now is because the next lab session is your midterm, I guess. Um, by then we would have released the third assignment, and you need scikit-learn for third assignment. Okay, so you cannot use this for the second assignment, but the third assignment is based on scikit-learn. Okay, so okay, there are a bit more questions in the chat, I guess, but let's get started. So then I will come back to your questions. So as I said, scikit-learn is an open source machine learning library. Okay, so that supports several supervised and unsupervised learning algorithms. So it has a bunch of, like, tools that we could use every day. Like, maybe I'll zoom in a bit more. Is this better? Do you see my screen better? Okay. Okay, so let's get started. So we are going to see first some examples for how to use scikit-learn for classification. Okay, then I will also show you how to use scikit-learn for regression, but that will give you pretty much the idea or the general framework of this package. Okay, now for today's tutorial, like, so we are going to use pandas to store our data, like in data frames, and we're going to use matplotlib for plotting things, and we're going to use numpy for the data matrices, and I guess you're already using numpy in your assignments, right? And this is again like color maps from the matplotlib. So these are the basic packages that we are going to use. So let's run this cell. Now, for the first example, we are going to use this data set. I think it was taken from Kaggle, where you have a bunch of information about people, like, on the social network profile, and, like, so you show ads to them. Now the labels or the target that you want to predict is whether they purchased based on that ad or not. Okay, so the idea here is, given someone's profile, can you predict if if they're going to click the ad and purchase something, right? So now, is this classification or regression? You can type your answers in chat. So this is classification, right? So okay, that is good. Let me post the link once again because I see a few more people joining. Okay, so this is classification, right? Like, so the target here is yes or no, like either they purchased or not. And as you can see here in this data set, the target is represented as 0 or 1, 0 for not purchasing and 1 for purchasing, right? So what are we doing here? So we have the data in the CSV file. Okay, the advantage of Panda is like you can do a lot of these data processing operations like in one shot. Like so here the pd.read CSV is going to read the CSV file and put it in the data frame. Okay, now if we do data adds.head of 20, it means like I'm going to print the first 20 entries. Okay, so the first entry is the feature names, like we have user ID, gender, age, estimated salary, whether they purchased or not, and we have printed the first 20 lines. So you see 19 examples, right? So you could print whatever number of examples that you want, and when you do dot shape, it's going to give you the shape of the data. So this is 400 data points with 5 columns, right? So I think the 400 includes the header too. So it's probably 399 data points. Okay, so let's just print 5 instead of 20. So you're going to see the first 4. Okay, so now we want to set up a classifier using this, right? So and there are a bunch of features. So again, I have a question. You can, it's easier to answer questions like by just chat because, well, so whenever I ask questions, you can post your answers in the chat. I will read the chat. So my first question is, can we use user ID as one of the features, like as one of the input to my classification algorithm? Okay, a lot of you say it won't be useful. No, right? So it's not a good idea to use user ID because user ID is unique. Okay, and it is just an ID, right? Like, so you cannot learn anything about the user by just the user ID. So we will ignore user ID. We will use the gender. We will use the age. We will use the estimated salary, and we are going to make a prediction of whether they purchased or not. Okay, so now we have an additional challenge here, which is the gender is male or female, right? It's not a numerical value. So if you remember our discussions in the class, like, so most of these algorithms that we use are mathematical models, and they expect some numerical features, right? So now how do we replace these male and female with numerical features? Like, one simple thing that you can do is just put 0 for male, 1 for female, or 1 for male, 2 for female, right? So we can do these conversions ourselves, or we can also make use of some of the pre-processing packages that are already available in Scikit-Learn. Okay, so here you see I'm using from sklearn.preprocessing import label encoder. Okay, so label encoder is a function, okay, which basically takes a column of like categorical values and gives you some label for that. Okay, it's like numerical values. So here I do label encoder.fit transform. I'm just sending the gender column of the data frame. Okay, and I'm replacing the gender column of the data frame with the transformed gender column. And as you can see here, now the gender has numbers 1 and 0. So probably 1 is male, 0 is female. Is that clear? So typically when you have a data set, like, you can, as a first step, do this pre-processing where you basically do label encoding for anything that is categorical. Okay. Okay, so now this is good. I still need to create my X and Y, right? So could we also replace, we could replace it. Okay, so that's what we're doing. So can we do -1 and 1? Yes, you could do those things too, right? Like, but in this case, there's no specific reason why one should be negative, one should be positive. So let's just do 0. Okay. Okay. So now I need to split this into input features X and output Y. So X is given by, I'm kind of in, like I'm slicing. Okay. The slicing operation in Panda is like dot ilog something dot values. Okay. So in all the columns, sorry, in all the rows, I'm just picking columns from 1 to 4. Okay. So this is 0th column. So 1, 2, so the last one is excluded. So it's going to pick 1, 2, 3, these 3 columns as X, and the 4th column as Y. Is that clear? Okay. Anything else in the chat? Okay. Would it be better to use one hot encoding for the gender? Right now it's treated as an ordinal value. Yes. You could do one hot encoding too. So there are multiple encoding schemes directly implemented in Scikit-Learn tool. So let's go to Scikit-Learn and search for one hot encoding, right? Okay. Okay, I have to check, but I'm sure there will be one hot encoding. Like if not, you could also write your own function, right? But in this case, this is not that serious problem because it is a binary value, right? Like, so in binary value, like 0 and 1 is okay. It's almost like the one hot. It is one hot just for one, like whether it just denotes presence of male or absence of male, which is female, right? So this becomes a problem only when you have like more than 2 possible values. Okay. Okay. So now let's try to print X just to see what is there in the X, right? Oh, I think I did not run some of these. So let's just run this, then I run this, then I run this. Now you see X has 3 things. Okay. And if you also print Y, Y will be, it's small y. Y is just a vector of all the labels. Okay. Okay. So now we have the data in the form of X comma Y. The next step is to create train test split, right? Like, so we want to train a classifier. So to measure its generalization performance, we want to split the data into train and test. Again, you can implement it by yourself from scratch, or you could use Scikit-Learn. So in this case, I'm using Scikit-Learn from Scikit-Learn.model selection, import train test split. Okay. So train test split is a function which takes X and Y as input. You need to specify the size of the test set. So here I'm saying, okay, I want 25% to go to test set and 75% to the training. Okay. And the random state is just for random shuffling, and it is going to return you 4 things. It's going to return you the X train, X test, Y train, Y test. Okay. So let's run this, and I'm printing just the shape of X train. Okay. There are questions in the chat. Just give me 1 second. I will post the. Okay, so we're in the next step before splitting, exploring the data distributions to choose an appropriate model. Well, that's a good question. That's a good part. So yeah, you could explore the data. So we're going to do a little bit of that very soon. Okay, so what probably you should not do exploring the data before you split, right? Because if you do this exploration before you split, then you are seeing the test set. So you're going to make choices which are based on the test set. So you don't want to do that before you split. Okay, so first you split the data. So now I have training data, so I can do all my explorations in the training data. Okay, So now one thing that we can already see here is the data, like in the data, the features are in different range, right? So this is small value. This is just 0 or 1. This is a number, 2-digit number, and this is a 5-digit number. Okay, so this kind of like situation where you have different range for different variables, often it's not a good setup, because now some weights are going to be small, some weights are going to be big, and some features are going to dominate. Okay, so you want to avoid this. So typically, like, you will do some pre-processing, like so there are a couple of options, like you could standardize the data or normalize the data. Okay, is that clear? uh, okay, isn't there a chance my training data has not same distribution as the test? Hmm. I don't understand your question. So do you mean you want them to be same distribution, or you don't want them to be same distribution? You can also unmute and ask your question.
Yes, so basically I want the test data. I guess I want the test data to have the same distribution for every feature that compared to the training data, right? But
Well,
in splitting just like this doesn't have a risk of
that's a
this
good question.
not being the case.
Yes, that's a good question. So we are going to talk about that. Like we can do better forms of splitting where you maintain the class distributions. There's somebody's already saying that you could use stratified split. Yes. So I'll show you how to do stratified split in some time. Okay. So for
Thank you, sir.
now, it is doing the most naive thing.
Okay, thank you.
Okay. So now, well, the first step is now that we have the data, like we want to standardize the data. Okay. So we want all these features to be in a similar range. Okay. We're going to do that by using normalization or standardization. Like, so to do that, let's take this simple data set. Okay, so here I have the number of bedrooms. So this is like going back to the house selling price example, right? Like, so that we saw in the class. Like, so here I have the square feet of the house and also the number of bedrooms, and I want to predict house price, let's say. And in this case, you can see that clearly there's a big disparity between the range of the number of rooms and the square feet, right? So there are a couple of ways in which you could normalize this. Like, so one is called min-max scalar. Okay, so this is basically simple normalization where you do x minus minimum value by max minus min. Is it clear? So again, you can implement this by yourself if you want, or you could use the sklearn preprocessing. So here I do from sklearn.preprocessing import min-max scalar. Okay, I instantiate the min-max scalar. Okay, so then I just do the min-max scalar dot fit transform. I give the data set, and it is going to scale things, and this is how the data looks like after after scaling. Is that clear? Now everything is in like similar range. Let's run it, and this is how it's going to look like. Okay. Um, okay, there is a very interesting question in the chat. So can we normalize before splitting? I want everyone to answer. So can we normalize before splitting? Can we do the normalization before we split the data into training and test set? Okay. Many of you say yes, but Savior says no. So Savior, can you tell me why no?
Well, I guess ideally you want to normalize on the mean of the training set. Well, you want to use the mean of the training set and then like apply the normalization on the test
Yes.
set afterwards.
Why? What's the issue? What's the issue in using the test set also for normalization?
mm, Like you would be kind of using the features of the test set on like the training process. I don't know like
Yes.
how to explain it.
Again, that is leak of test set, right? Like, so if you use the entire data set to do this normalization, then you're finding the min value and max value based on both the training set and test set. So that is against our initial goal, which is I'm going to keep this test set separately and I will not see. So if you want the test set to be true proxy for generalization, then you should not touch the test set for anything. Okay, so this is the reason why we first split and then we do this. Okay, so as Xavier rightly mentioned, like, so you do this with the training set, then you apply the same scale to the test set too. Okay, so we're going to see how to do that soon. Okay, but there are a couple of options here. You can either do normalization or you can do standardization. Okay, so standardization means you do this equation like x minus mean by standard deviation. Okay, so when you do standardization of the data set, here you see both positive and negative values, because standardization means I'm making the data zero mean and there's going to be a standard variance. Is that clear? So sometimes normalization is useful, sometimes standardization is useful. It really depends on the task. Okay. Now I'm going to do that for the data set that we are working with. Okay. So for our data set, as you see here, I take the X train, I do the transformation. Okay. Then a couple of things are going on here. So when I do fit transform, the transformation operation is going to learn the min and max from the data and also transfer the data. Okay. So then for the test set, I can just apply by saying, okay, I want this dot transform of my test data, and it's going to give me the transform data. Okay, so there is a difference between fit transform function and transform function. Fit transform means you're using this data to find the min and max, then you do the transformation. Okay, transform just means you're doing only the transformations on and the min and max comes from the training set. Is that clear? Okay, so this is good. So now we have standardized the data. We run it once more time. Okay, so before we get into the classifier, I have a couple of helper functions here. These are mainly to visualize the data and the classifier. Okay, so I'm not going to get into the helper function. I think you have seen similar visualizations already in first assignment. You will see some of them in second assignment too. So I will let you read this by yourself later. Okay, so if you want to know how the visualization is done. So let's directly go to the classifier. Okay, as a first example, we are going to look at naive-Bayes classifier. Okay, the one that we just saw yesterday in the class, right? Like, so I'm going to do Gaussian naive-Bayes. Okay, so as you see here, all these naive-Bayes classifiers are implemented in Scikit-Learn.naive-Bayes. Okay, so from Scikit-Learn.naive-Bayes, I import Gaussian naive-Bayes. Okay, now you can actually go to the documentation. Okay, to see what are the different algorithms, naive-Bayes algorithms implemented in Scikit-Learn. Okay, so you see my tab, right? Like the Scikit-Learn tab now. Okay, so here you see they have is naive-Bayes dot Gaussian naive-Bayes, which is what we are using now. They also have, well, I think I'm not looking at the, okay, I'm not looking at the documentation. Okay, now we are looking at the documentation. Okay, so that was a release note. Okay, so here you see that there are 5 different naive-Bayes methods implemented in this scalar, like this Bernoulli naive-Bayes, categorical naive-Bayes, complement naive-Bayes, Gaussian naive-Bayes, and multinomial naive-Bayes. Okay, so given that we have real features, So we're going to use Gaussian A-base. Okay. Now, this is the general recipe for using any Scikit-Learn model. Okay. So the first thing that you will do is import that particular model. Like if you want Gaussian A-base, you import Gaussian A-base. Then you create an object of that class. So NB classifier is Gaussian A-base bracket, right? Now this NB classifier is one of the objects of this classifier class. There are two main functions in every machine, like every algorithm implemented in Scikit-Learn. Okay, so one is called fit, the other is called predict. Okay, so you will use fit to learn the parameters of the model. Now, if you think about it, in the class we did a complete derivation of Gaussian A-base. Like now, in your assignment, you're going to implement those equations by yourself. But in Scikit-Learn, all those equations are implemented for you already. Okay, so you just do classifier.fit of x comma y. Now this operation is going to learn the mu, sigma, pi, everything that you need for Gaussian A-base. Is that clear? So once you do that, then you can use the model to make predictions by just calling classifier.predict. So I do classifier.predict, I pass x test, and I get y prediction. Is that clear? So these are the four important things that you should know. Once you know this, you can literally replace Gaussian neighbors with whatever algorithm you want. Okay, so you can do k-nearest neighbor. You can do linear regression. Like so, we are going to see a bunch of new algorithms in the next few weeks, like logistic regression, neural network, SVM, etc. Okay, so you can use any algorithm that you want by just importing it and instantiating it, and these two lines are same. For all the algorithms, you always do fit and predict. Okay. Sometimes when the classifier has hyperparameters, then you will pass those hyperparameters in this line. For example, for Gaussian neighbors, there is no hyperparameter, right? But with k nearest neighbor, there is a hyperparameter which is k. So you will call k nearest neighbor with k is equal to 2 or with k is equal to 5, etc. Is that clear? Okay, so there is a question. So why doesn't it return something when it fits? Well, I think that's just the design choice. Like so, you fit, everything is there in the classifier. If you want, you can actually extract those parameters from the classifier. Okay, so let's actually try to go to the Gaussian naive-Bayes. Okay, so in the Gaussian naive-Bayes, you see here, it has a bunch of attributes, but I'm pretty sure you can also get the params. So see, when you do the model dot get params, you are going to get the parameters. So if you go to get params, you see it's going to give you all the parameters of the model. Is that clear? Okay. So now I trained a model in this single line, right? So it's so easy. This is why I said I should not have done this tutorial before you finish second assignment. So I trained the model in one line. So then I also made the predictions. So what is the next step? So what is the next step? You can post your answers in chat. We need to check the performance, right? We need to compute the metrics that we care about. Well, not RMSE because we are doing classification right now, right? So we are going to do accuracy. Okay. So Scikit-Learn actually has all the metrics implemented in something called Scikit-Learn.metrics. Okay. So again, if I try to go to Scikit-Learn.metrics, okay, I should go to the right thing. Okay. Yeah. So if you go to Scikit-Learn.metric, you see there are a whole bunch of metrics available for classification. So far in the class, we have only seen accuracy. Okay, we are going to see a bunch of other metrics in the coming weeks, and you also have a bunch of metrics for regression. I think for regression, we looked at mean squared error, right? But they have a lot of other types of errors too, if you want. Okay. Okay. Now let's go back. So from sklearn or metrics, I'm importing accuracy score. Okay. And I'm also importing another metric called confusion matrix. Okay. So this confusion matrix actually looks very similar to the loss matrix that we saw in the class yesterday. Okay. Let me explain how it is going to look like when we see the example. Okay. So I can compute the accuracy score by just passing the true target, which is y test CLF, and the prediction of the model. Okay. And that is going to give me the accuracy. Now you can do the same thing and get confusion matrix. So if I print these things, you see that this model has 89% accuracy, not too bad. And this is the confusion matrix. Okay. Now what is confusion matrix, right? Like, so typically in classification with like 3 or 4 classes where you can visualize this matrix, it's very useful. So if you look at the matrix, what this really means is in the rows you have the true class, in the columns you have the predicted class. Okay, so this matrix tells me that 67 class 1 examples are predicted correctly as class 1. Okay, there's one class 1 example which is wrongly predicted as class 2. Okay, similarly there are 22 class 2 examples that are correctly predicted as class 2, and there are 10 which are misclassified. Okay, so now you can understand why this is called confusion matrix. This is called confusion matrix because these numbers tell you how, like basically what fraction of examples the model confused with other classes. Okay, now can you tell me how would an ideal confusion matrix look like? You can post your answers in chat. How would an ideal confusion matrix look like? Okay, it would be diagonal, right? So ideally it will be diagonal because the diagonal is the correct classification. So all the numbers will be in the diagonal and the rest of the entries will be 0, right? So that is what an ideal classifier's confusion matrix is. So basically we're looking for a matrix that looks very close to diagonal. Okay, this is not a bad matrix because there is not a lot of confusions happening. The performance is pretty good already, right? Now let's try to visualize this classifier. Okay, so here is the visualization. This is where the helper function is used. So I have created this helper function, the model visualization, which visualizes the classifier. But the only thing is there are 3 features, right? Like, so we had age, salary, and gender. So it will be a 3D thing. So just to make things simpler, I made it 2D by considering one graph for male and one graph for female. Okay, so for the male set of the data set, this is all the training data points. Okay, so red is 0, 1 is green, right? There is 0 class and 1 class, and this is how the naive Bayes classifier would look like. Okay, now as you can see, this naive Bayes classifier, this Gaussian naive Bayes classifier it has non-linear decision boundary, right? Now what can you say about the covariance matrices for different class conditional densities? Do you think I shared them or I did not share them? Okay, they are not shared, right? Like if I had shared them, I would have received, like I would have seen like a linear decision boundary. So this is an example where the covariance matrices are not shared, and they are also diagonal. Okay, so that's what the naive Bayes assumption is. Okay, so and I think this is for the this is for the test. This is for the training set, and I can also do the same for the test set. Okay. Okay, I think that concludes our discussion on how to do naive Bayes using a scalar. Any questions? So, so this is the main part of the tutorial. Okay, so I have told you how to use for one classifier. Now we are just going to see how we can use the same setup for different classifiers. Okay, so any questions so far? You can unmute and ask your questions too. Okay, well, hopefully it was clear. So now let's move to how to do k nearest neighbor. Okay, so now I'm going to go very quickly over different classifiers. Okay, so in this case, let's run this. So from Scikit-Learn.neighbors, so neighbors is what has all the nearest neighbor algorithms. So let's actually see what are the different algorithms in Scikit-Learn neighbors, I guess. Oh, okay. So here you see a whole bunch of neighbors algorithms, right? Like the simplest is k nearest neighbor. But k nearest neighbor, well, as you're going to implement k nearest neighbor in your second assignment. By the way, have you guys started looking at the second assignment? Okay, you should. So you will, as you will experience in your second assignment, k nearest neighbor is very slow. Okay, because every time you want to do the nearest neighbor search, that's computationally very expensive, which is why we have a lot of these other algorithms. Like, so there are faster approximations of neighbor search by using things like ball tree, KD tree. These are different data structures that will help you to find approximate nearest neighbors quickly. Okay, or nearest centroid approach, etc. Okay, so for simplicity, we're going to use k nearest neighbor. So from scalar.neighbors, import k neighbor classifier. So now you see that I'm passing a hyperparameter, right? So if you want to know what are the hyperparameters for the classifier, then you just need to go to the classifier, okay, and look at the parameters of the classifier. Okay, so I think it's a bit confusing. So these parameters are parameters that you pass to the classifier. So technically they are hyperparameters. Is that clear? So you see n neighbors, which is by default 5. You can change it if you want. There are a bunch of things. Usually you won't touch most of these things. But there are, for example, there are things like n jobs, which is the number of parallel jobs to run for nearest neighbor search. So if you do that, you're going to speed up the search. Okay. We will not touch any of these things mostly. We will mostly use the number of neighbors and also this one p, which is useful. So if you set p to 2, that is the Euclidean distance. You could set p to 1, then you get a different distance, etc. Manhattan, etc. Okay, so there's a question: is there a function in SQL that helps find the most optimal hyperparameters? Yes, so we are going to do that. We are going to see how to do that soon. Okay, so I pass this hyperparameter, then I do fit, then I do predict. Okay, and here I predict the accuracy score and confusion matrix. You see KNN has 90% accuracy, and this is how the confusion matrix looks like. Okay, it's a bit different from naive Bayes, but still in a similar range, right? So then you do the visualization. So I'm not going to run this once again, because when you run it yourself, you will see that this visualization is very slow because KNN runs very slow. Okay, so it will take a minute. So let's not waste the time. So this is how the k nearest neighbor looks like. I think in this case we used k is equal to, what did we use? We used k is equal to 2, right? So I used k is equal to 2. This is how the k nearest neighbor looks like for male and female categories. And this is with the test set. Okay, that's it. So now you can do that for any other classifier. Okay, so in the interest of time, and also because we have not seen these classifiers in the class, so I'm not going to go through these in detail, but I have given you the code for how to do this with logistic regression, which is a classifier that we will learn in the next week class. Okay, And we have a whole bunch of other classifiers like support vector classifier with kernels, decision trees, random forest, etc. Okay, so we will see all these classifiers in the class in the coming weeks. But maybe let's just open one of them, right? So let's just open, let's open decision tree. So in decision tree, you see it looks exactly like other classifiers. The only thing is I'm calling decision tree classifier from the tree package. And for this, there's a hyperparameter, which is criteria. Okay. Otherwise, everything looks same. Okay. So now let's go in detail how to do hyperparameter tuning, which was the question in the chat, right? So in the class, we learned about cross-validation. And in your first assignment, you did k-fold cross-validation by hand. Not by hand, but from scratch, right? So the nice thing with Scikit-Learn is like you're going to see a whole bunch of cross-validation techniques already implemented for you. And you can just call everything with just one command. Okay, so let's see some of them. So first we are going to do k-fold cross-validation. Okay, so I don't need to explain what is k-fold cross-validation now. Like we have seen that in the class, you have done that in the assignment. So I'm directly going to show you some examples. So I want to do k-fold cross-validation. Well, let's just do two-fold cross-validation. Okay, with this toy data set. I have a data set which is a bunch of labels ABC. So there's A, B, B, C, 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 C. Okay, this is my labels. These are my labels. Okay. Now from sklearn.model selection, I import k-fold and I define my k-fold classifier here. I say, okay, number of splits 2. I want 2 splits. Okay, and I don't want you to shuffle. If you can shuffle if you want. Now for train indices and test indices in k-fold dot split of x comma y, so k-fold dot split of x comma y is going to give you a bunch of splits. Okay, and I'm just printing those splits here. Okay, as you can see here, this is the first split and the rest is the next one is the second split. Okay, so you see the problem here, right? I think this was the question raised by one of the students in the beginning. So if you split without any care, you might end up with splits that looks like this. See, the training set has just C's and my test set has A, B, C. This is a bad split, right? So this kind of issues happen because there is a class imbalance in my data. If all the classes are equal, like in terms of the size, then maybe we won't have this issue that much. But when you have class imbalance, this is a serious issue. Okay. Now this is why you should do stratified k-fold. Okay. Now what is stratified k-fold? So in stratified k-fold, I will first split my data based on the class labels. So this is one class. I think this is A class. This is B class. This is C class. Okay. Now within each of this class, I'm going to split the data equally and use those to construct my train and test. So what I'm trying to make sure here is both training data and the test data has same class distribution. Like I want both to have, for example, 10% A, 30% B, 40% C. Okay, if that is what the true distribution is, I want both training and test to have the same distribution. Is that clear? Okay, so now I'm running the same example, but this time with stratified k-fold. Okay, so with stratified k-fold, oh, what happened? Did I run this correctly? Let me run this. Let me run this. And let me run this. Okay, I think I did not run that before. Okay, so when I do stratified k-fold, you see that there is a reasonable split of the classes. Okay, is that clear? So there's a question in the chat. So should we start here for the target value labels and not really for the layer? Target value. What do you mean? Like, so target values are the labels, right?
Yes, yes.
Okay.
Oh,
So
I
that's
meant not the features. Sorry.
no, we're not stratifying for the features. Why would we stratify for the feature? Right? Like, so like it is more important that we, okay, our goal is to learn the target, so it's more important that we have good representation of the target in both X and Y. Okay. Of course, it would be nice if you can also stratify for features, but it is not essential.
Okay, thank you.
Okay, so this is about splits. Okay, now about hyperparameter search, there was a question, right? So is there anything in the Scikit-Learn which helps you to run and find the optimal hyperparameter, right? So I'm going to show you how to do grid search. Okay, okay, is stratification only used for categorical data? That's a good question. So I think you could stratify for regression too. Like, so I don't know if SQL has implementations of that, but you could have bins and try to make sure that there are enough examples in each bin in training and test, right? So you could stratify for regression too. That's not a bad idea. Okay. So now we are going to look at grid search, but before that, let me also show you what are all the different model selection strategies SQL has, right? So you see it has a lot of model selection strategies. Like, so there's leave one out cross validation that we saw in the class, right? Then there's k-fold cross validation, group k-fold. I don't know what that is. There's leave p out, shuffle split. There are a bunch of stratified versions of all those things. And there's splitter functions, and there are a bunch of hyperparameter optimizers. Okay, grid search, random search, etc. Okay, so let's start with grid search. So let's say I want to optimize the hyperparameters for my k nearest neighbor classifier, and I have two hyperparameters that I want to like optimize. One is nearest neighbor. Okay, I'm considering 10 different values for nearest neighbors: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right? And for the distance, I want to try both Manhattan distance and Euclidean distance. Okay, so the first thing that I'm doing here is like I'm doing stratified k-fold. Okay, number of splits is 3, so I do 3-fold cross validation. Shuffle is equal to true, and this will have all the stratified data. Okay, so now you will see that this is okay. So whatever you see in these 3 lines, right, if you implement it by yourself, you're going to use probably a few hundred to 1,000 lines of code. Okay, if you want to do it properly. So everything is implemented for you. So what it does is like it first splits the data. So then I'm calling this grid search CV. Okay, so I pass, okay, what classifier I want to do grid search on. I want to take a k nearest neighbor classifier, and I want to find the right hyperparameter. And what are all the parameters I'm tuning? These 2 parameters. Okay, and on what criteria I want to do model selection, accuracy. You can change it to whatever you want. And the data is here. Okay, so this grid search is going to do 3-fold cross validation for each possible combination of this hyperparameter. Okay, so how many combinations are there? There are 20 combinations, right? It is going to train 20 different k nearest neighbor classifier. Okay, and it's going to return you the best configuration. Okay, so then you can simply do grid search.fit of whatever, right? So maybe instead of calling this as grid search, I can also call this as my classifier. Okay, so then this becomes classifier.fit. Okay. Okay. Sorry. Maybe I should not do that because then I will mess up with the rest of the cells. So let's just keep it like that. Okay. I don't want to run it now because it takes time with k-nearest neighbor. Okay. So now here you see the best parameter set that was found. If you want to know what was the best parameter, you just do grid search dot best params underscore. It tells you that, oh, k nearest neighbor with nn is equal to 5, k is equal to 5, and p is equal to 2 was the best. Is that clear? You could also print all the grid search values. Like, so for every combination, what was the accuracy? If you want that, there's a way to look at it. Okay, in case you want to do a more detailed analysis. Okay, and there is also something called classification report. Okay, so classification report, when you pass the predictions and the model's true value, is going to give you a report like this. Okay, so maybe right now you can't make a lot of sense from this report because we haven't seen all these things in the class. So we are going to see them hopefully next week or the week after. Okay, so for classification there are many metrics that we could think of, not just accuracy. You could think about precision, recall, f1 score, etc., and then there's micro averaging, macro averaging, and all those things. Okay, so this gives you a complete picture of every metric that you would care about, and it is all implemented in just one function. Is that clear? So I think that concludes our discussion on classification. I also wanted to quickly show you regression. Okay, so this is basically redoing your first assignment, but with a Scikit-Learn. Okay, so here again, I'm going to take this regression task where given the position and the level, I want to predict the salary. Okay, now position is a bunch of like categorical things, right? Like, so you could modify it if you want, but I want to show you visualizations. So I'm just going to take one feature. So my feature is going to be just the level. Okay, so given the level of the employee, predict the salary. Simple regression task, right? So that is what the slicing is doing. So the slicing takes the level and put it in X, salary and put it in Y. Okay, now I have some visualization functions. That's fine. So here is how it looks like. I think I might have normalized it, right, at some point. No. All right. Okay. So to do regression, you're going to call linear regression from linear model. Okay. So from sklearn.linear model, you import linear regression. You fit X and Y. Okay. So, and this is how the line looks like. And you can compute. I'm not doing RMSE here, but you can do from the metrics. You can use RMSE and compute RMSE if you want. Is that clear? So similarly, you can also do polynomial regression. Okay, so for that, you're going to do from sklearn or pre-processing, you import polynomial features. Okay, now polynomial features, like you decide what degree you want. So in this case, I say degree 2. Then you transform your X. Okay, so then you define your model. So the model is still linear regression. I fit this data, and this is how it looks like. Is that clear? Okay, so I think we finished on time. Any questions? Well, I did enjoy doing the tutorial myself. Maybe I will do the tutorials myself instead of giving it to the TAs. Okay. There is a question in the chat. There are a couple of questions. So why did we split the extra? Oh, okay. So yeah. So I think this was just a last minute. I think this example was put together last minute, so we don't split things, but you can do those things. Okay, so here I was not at all evaluating the test performance. So if you want, you can do train test and measure the performance in test by yourself. Okay, there was a question before that. So is there any function to suggest good models to use based on distribution analysis of the data, or do we have to figure that out by ourselves? Well, that's a good question. I think scalar algorithm cheat sheet. Yeah, I remember. Okay. I don't recommend this by like I don't seriously recommend this. Okay, I'm just showing you that there's something like that that exists in Scikit-Learn. So I think it's a cheat sheet to decide what algorithm to use, but I think this is a very naive cheat sheet. So I don't think it's very useful because you yourself will know whether to do classification or regression. You don't need a cheat sheet to figure out what to do, right? Like so. Um, there is no automated way of figuring out which is the right model to use. Okay, so often you will try different models, and also it comes really by experience. The more projects you do, the more practical things that you do, like you are going to figure out which model works, which model doesn't work, right? Like so I highly encourage you to try Kaggle competitions. Like so we are going to have a Kaggle competition by the end of this course. Like so the course final project is a Kaggle competition, but once the course is over, like you can go do more Kaggle competitions if you want to get a good hold of matching data with models. Okay, anything else? Okay, so then I think we can finish. So the recording, well, the tutorial is recorded, so I'm going to put the recording out for people who couldn't join. And please start with your second assignment. It takes time. There's a question. I'm wondering the full solution is rather etc. Okay, so we don't provide solutions for assignments. Like so, like you'll get feedback on what you have done, but we will not be providing solutions. Okay, so we will stop here. Thank you.